Okay, so we have the nonlinear Schrodinger equation, the cubic, in one dimension, and we want to find solutions of this kind, ei omega t phi x. So, if we put this in the equation, we will have that here we'll have I omega ei omega t phi x equal to minus ei omega t phi prime prime plus or minus, well, here we obtain phi squared phi ei omega t. Okay, so we can get rid of this, and this. Okay, and we will obtain minus omega phi equals to minus phi prime prime plus or minus phi absolute value squared phi. Okay, so if we write phi of x as 8 multiplied by ei theta, that you can consider eta as the absolute value of phi. Okay, so we'll obtain minus omega eta ei theta equal to, okay, minus, and we will have to derive and ei theta 2 times minus and plus, here we will obtain eta to the third ei theta. Okay, so we would have to make the derivative 2 times of this. That is some work, but after you make all the work, you arrive to this, an expression that has some terms that are real and some that are imaginary. So we will have two equations if we separate both parts. Okay, so after making all that, we will have that 0 is equal to minus 8 two derivatives plus 8 theta prime squared plus or minus 8 third plus omega 8, and the complex, the imaginary part will be 2 8 prime theta prime plus 8 theta prime prime. Okay, if we multiply this expression by 8, okay, we will obtain the following expression: 8 squared theta prime prime equal to 0, meaning this, that, well, what is inside theta squared theta prime is equal to, let's say, L, a constant. Okay, so if we solve for theta prime and we replace in the first equation, we will obtain minus theta prime prime plus L2 L squared 8 minus 3 plus or minus 8 third plus omega 8 equal 0. we can multiply this by eta prime. Okay, eta prime plus omega eta prime. Okay. Okay, so this term is going to be equal to 1/2 eta prime squared prime. Okay, and the next one is going to be L squared over 2 eta squared prime. The next one plus well, it can be minus also. We will say with plus 1 over 4 n fourth prime, and the last one will be omega 1/2 eta square prime all equals 0. So okay, so let's now define h of eta prime equal to, well, 1/2 of eta prime squared plus L squared over 2 eta squared plus eta to the 4th over 4 minus 1/2 omega eta squared. Okay, as you can see, the h of the x will be equal to, well, 0. You can see it here, and this means that h will be a constant. Okay, so now let's call tau of x equal to eta prime of x, and so tau prime x will be equal to eta prime prime of x. Okay, and we'll call this b eta. So what we just seen so is that eta x and tau of x h is a constant, and so we can call this constant e. This is looking just like a Hamiltonian, where here we can say that this is a potential, and this can be seen as a kinetic energy. So now, if we suppose that L is not 0, okay, so if exists, let's say, E, such that h of eta tau is equal to E, okay, for all x in, let's say, R, then we have to say that recall what eta is. We have the solution uxt, the depth value, is actually what we at the beginning we called absolute value of phi, which would be eta, and we are expecting that our solution, as we saw in the last videos, is in L2 of R. So we are expecting that our solution has to be in L2R. So we're going to see that if we are asking this and this, it cannot be possible. If we want that the limit of eta when let's say x goes to plus or minus infinity be 0, then we will need that L to be equal to 0 and E equal to 0. You can see here this term will disappear and the other terms will be equal to 0. So knowing this, L equal to 0, our remaining potential V of eta will be equal to n to the fourth over 4 minus 1 over 2 omega and eta squared. So this will be equal to eta squared over 2 eta squared over 2 minus omega. Okay, so if omega is negative, we will have a potential that is something like this, and if omega is positive, sorry, this has to be 0, negative and positive, then it will have 2 roots and will be something like this. Okay, so these are the diagrams of the potentials through the etas. So you can see that in this case we have a, let's say, eta minimum. Okay, one can see that this is going to represent the solutions where the energy is B of atom minimum, which are the ones that are going to be in L2R. Okay, where the energy is going to be equal to 0, L is going to be equal to 0. So knowing that, we can go back to the equation and solve for n prime. That's going to be eta prime. That will be equal to the square root of omega eta squared. Well, if we see both cases, we can have plus or minus 1/2 eta to the fourth. Okay, and that is going to be equal to plus or minus square root of omega eta square root of 1 minus 1/2 eta squared. Okay, so here is missing a omega squared. Okay, no, omega without the square. And so then we can integrate. We will have that it will be equal to the integral of the eta 1 minus eta over, well, we can say square root of 2 omega all to squared. Okay, this will be equal to, okay, now for the next equality we have to make a change of variables. We'll take that z is equal to eta to square root of omega, and dz will be the eta over 2 omega. After making that change of variable, we will obtain the integral of dz to 1 minus z squared. This will be equal, after making all the changes, to square root of omega integral dx, and this will be square root of omega x plus c. So after obtaining that, obtaining the eta, and knowing that L was a constant, we know now that U is equal to E minus I omega t eta x ei theta 0, knowing that theta was a constant, because L was a constant.